All right, good afternoon, everybody. Welcome to the 2023 Spring Semester Distinguished Lecture Series, of the ECE department. And it's my great honor to introduce our speaker today, Dr. Robert Calderbank. Dr. Calderbank directs the Rhodes Information Initiative at Duke University. He is a distinguished professor at Duke. He has such a rich experience in both industry and academia. Before he joined academia, he was a VP research at AT&T. And after that, he joined Princeton University as a professor before he moved to the Duke University. He's well known in many areas, and look at, for example, the quantum area. He is an inventor for this CSS code, which is named after him, and it has been used widely in quantum computing. Dr. Calderbank is a member of National Academy of Engineering. He is IEEE fellow. He's a fellow of AIS, and he received many prestigious awards, including the IEEE Hammond Medal and 2015 Shannon Awards. And he has done so much work in multiple of those areas. I think I can keep going for another hour, just talk about his achievement, go down his CV. But let me just stop here and let's welcome our distinguished speaker today, Dr. Calderbank.
Well, thank you very much for a very generous introduction. So today's talk is not about quantum, it's about wireless. And so, as you probably know, there are generations of wireless technology. And what I'd like to suggest is that each new generation is an opportunity to think afresh about fundamentals. So let's think about what happened in the past. Well, there was a transition from narrowband TDMA systems like IS-136 to CDMA, and that was driven by the power of spreading. A little later, there was a transition from CDMA to OFDM, and that was driven by the power of reacting to instantaneously to channel gains. What's happening today? Well, channels are getting more and more difficult to learn, and Doppler shifts are getting more and more dramatic. And I'd like to suggest it's an opportunity to develop new theory. Now, I should say at the beginning that this is not a math talk. And so at some point you might say, well, where did you hide the equations? And the equations are hidden in these two magazine articles. So if you're curious about the equations, please check out the two articles. Should say at the beginning that I'm going to be talking about a modulation called OTFS. It's a waveform that is being promoted by Cohere Technologies. I'm on the technical advisory board of Cohere Technologies, so full disclosure. So what I've done here is in the picture, you can see the generations going up and to the right. And I've organized channels of interest by Doppler spread. So terrestrial pedestrian channels, essentially no Doppler. Mobile terrestrial channels, 300 Hertz. If you were going to do mobility in millimeter wave, maybe 3 kilohertz. Then there's planes and there's random access satellite, where you might get up to 80 kilohertz. Anyway, today we design wireless systems using mathematical models. So how does that work? We have a mathematical model for the channel. We keep that mathematical model in mind, and we estimate the channel. And once we've estimated the channel, we do symbol detection. So I'm going to refer to that as model dependent. And what I'd like to suggest is that this approach is losing ground as our channels become more and more complicated. Doppler becomes more and more significant. And I'm going to ask the question whether it might be possible to operate model-free. Let me try and explain what I mean by model-free. So we've asked this question, model-dependent versus model-free before. You can think of Newton's laws of motion as a model-based approach that develops understanding at the most fundamental level. And you can think of Kepler's laws of planetary motion as a model-free approach that, that uses data to make predictions. So you can say, well, what's changed since the 17th century? And what's changed is that machine learning has revolutionized image and natural language processing. Data-driven discovery has revolutionized bioinformatics. And machine learning has even revolutionized mathematics. I mean, mathematicians used to think of functions in terms of smoothness. How many times could you differentiate them? Now they're starting to think of them in terms of how closely can you approximate a function with a particular class of neural networks. There's a lovely article by Weinan in the Notices of the American Math Society that talks some more about this. All right, so now we're going to start talking about communications and radar. And so this is a picture of Philip Woodward. And Philip Woodward died in 2018 at the age of 98. And he was a very distinguished radar engineer and a virtuoso clockmaker, as you can see from the picture. And in 1953, which was only 5 years after Shannon's landmark paper on communications, he wrote a book on the information theory of radar. And he had a very particular point of view. He said you should look out and you should think of a radar scene, not as a radar scene, you should think of it as an unknown operator. That's a mathematical operator. And when you send a waveform to probe the scene, you should think of that as a question that you ask the operator. And so how should you think about radar detection? You should think of it as a game of 20 questions with an unknown operator. And so the question is, how do you design a good question? And this is the sort of function, this is the sort of signal that we're going to be looking at in this talk. What is this? So there's a sequence of pulses, that's called a pulse train. And the pulse train is modulated by a tone. So I'm going to call those pulsones because it's a combination of pulses and tones. And I'm going to be, from a communications point of view, I'm going to be looking at channels that delay signals in time and shift them in Doppler. And I'm going to want to show waveforms that are good at predicting those channels. So let's have a first conversation about channels. So here you see I've got a signal x of t, and I send it out into the world, and it bounces off these reflectors. And each reflector delays the signal by a certain amount. And if the reflector's moving, it gives it a Doppler shift. And on the right, I'm saying that I'm going to want to think about all of this, what's happening in the delay Doppler plane. I'm going to want to think in terms of taps. So I might have a tap that delays by tau 1. And you can see that red tap, that's where it's situated. The height of the tap tells you about attenuation from the reflector. So big tap, more energy, small tap, less energy. What I'm interested in doing is predicting the input-output relation from the response to a single pilot waveform. So I'm going to, in the talk, I'm going to make a distinction between estimating channels and predicting input-output relations. In a sense, channels are cause and input-output relations are effect. And I'm going to say we can give up on causes. All we need to care about is effects. All right, what constitutes a good question? So here, waveforms are questions, returns are answers, our objective is prediction. If we have a channel that just delays things, it doesn't do any Doppler shifting, then a time domain pulse is a good question. Similarly, if we have a channel that just shifts in Doppler, a tone, a frequency domain pulse, that's a good question. Now we're going to have, in wireless, we have doubly spread channels. They shift in delay, they shift in Doppler. And I'm going to suggest that a pulse in the delayed Doppler domain is a good question for such a channel. Now, I have to, what is a pulse in the delayed Doppler domain? Well, this is the start of the explanation. Now, there's an obstruction to defining a pulse in the delayed Doppler domain. It's called the Heisenberg uncertainty principle. It says that you can't simultaneously localize in delay and Doppler. So what do we do? Well, short answer is that we cheat. How do we cheat? We introduce quasi-periodic functions. So if you see here, there's a pulse in that central box. And every time, and there's a delay period, tau p. And when we move along the delay axis by an integer multiple of tau p, we apply a phase. When we move in Doppler by an integer multiple of the Doppler period nu p, we don't add a phase. So this is my quasi-periodic function. And you see I've cheated because it's like I'm localized in that middle square, but I'm not globally localized. This quasi-periodic thing spreads me out. So I'm technically not in violation. What's the relationship between a pulse in the delay Doppler domain and its time domain realization? So here, how do we get from the delay Doppler domain to the time domain? Well, the answer is that we apply a transform. What's the transform? It's called the Zach transform. This is the Zach time transform, so it's Z sub t. And there's a little bit of mathematics there as to what it is. But let's look at the parameters of the pulse. So the pulse spreads by 1 over b in delay and 1 over t in Doppler. B is the bandwidth, t is the time duration of the pulse. And if you look up at the time domain realization, you'll see that each little pulse spreads by 1 over b. You'll see that the little pulses, they're spread tau p apart. That's the delay period. The pulse is situated at tau 0, nu 0. Tau 0 tells you where the pulses start. Nu 0 tells you about the frequency of the modulating tone. So that's the relationship between the two. Now, we're going to suppose that there's a relationship between tau p and nu p. We're going to suppose that tau p nu p is 1, so that as we move tau p, we live on a hyperbola. And what I want to just note is that the two ends of the hyperbola are time division multiplexing and frequency division multiplexing. Because if you think about time TDM, time domain multiplexing, that's a limiting case. Why? You let the delay period grow, the pulses get further and further apart, the time structure disappears, and all you're left with is a single pulse at tau zero. FDM, that's a limiting case too. You let the delay period shrink, the pulses get closer and closer together. In the limit, the pulse structure disappears, and all you're left with is the tone. And so this hyperbola, you can traverse the hyperbola, and you can go from TDM to FDM. You can do it really smoothly. So now Woodward asked this question of, says, what's a good question? Well, a way of making that precise is to say, well, what constitutes an ambiguous answer? Well, if you're a radar engineer, you measure ambiguity in a very precise way. You send a signal S, and you correlate that signal that you send against shifts of the signal in delay and Doppler. That gives you the function ASS tau nu. You take the squared value. That's the squared ambiguity surface. And here, what I've done is I've just illuminated the ambiguity functions for TDM and FDM. So for TDM, what I've done is I've taken a single pulse, I've put in a sync transfer, a sync transmit filter. You can do the math and you can figure out that the ambiguity function is proportional to that green function there. Now you can think about the delay spread of your channel. It's approximately 1/b, so that you can separate targets that are 1/b apart in delay. Doppler spread, unfortunately, is a little different. There, the Doppler spread is approximately b, so you can only separate things if they differ by more than b in Doppler, and that's kind of hard. So the green ellipse there, which is TDM, it's a long ellipse. You see its width is 1/b, so you can separate things that are 1/b in delay, but its height is b. And so it's really smeared out in the Doppler axis. FDM, same thing, it's just a horizontal pulse instead of a vertical pulse. Okay, now then. So these two slides are really about, they're about localization in delay and Doppler. And I'm going to go back 70 years to Woodward. Now, this squared ambiguity surface that I introduced before, the volume under that squared ambiguity surface, that's something you can't avoid. There's something in radar called Moyal's identity, which is the Heisenberg uncertainty principle in another form, that says that that volume is like the squared, it's like the energy in the signal. What do radar engineers do? They can't avoid this volume, but they move it about so that they can see targets in certain ranges more clearly. So that's radar engineering, unfairly characterized. What did Woodward do? He started out with the ambiguity function of a narrow Gaussian pulse. That's the red ellipse that's shown there. And that's not a very nice ambiguity function. If you're a radar engineer, you don't want that function. What he did was he took a train of Gaussian pulses and he put them under a broad Gaussian envelope. And then he calculated the ambiguity function. And what he did was he redistributed the volume under the squared ambiguity surface. So the red ellipse becomes the little black ellipses. And suddenly, he's gotten rid of radar ambiguity. If you look at that blue square, the base and the height of the blue square are given by the widths in the two Gaussians. And if you're in the blue square, you can separate targets. Now, this trick of modulating a train of narrow things with a broad thing, just hold that in mind, because this pulsone that I showed you has very much the same structure. That's the ambiguity function of a pulsone. We have a blue box in which we've gotten rid of radar ambiguity. And the width of the blue box is the delay period, and the height is the Doppler period. And what is this function? We've got little narrow delay domain impulses. They're separated by the delay period tau p along the delay axis and by nu p along the Doppler axis. Each impulse has a spread of 1 over b along the delay axis, 1 over t along the Doppler axis. So if you invest more bandwidth or if you invest more time, you can shrink your ambiguity in the way that you would expect. And the blue rectangle is the fundamental period. So how should you think about the fundamental period in radar terms? So you're looking out at a radar scene. The radar scene has a certain delay spread, and it has a certain Doppler spread. You're looking for targets that are moving at a certain speed. And as long as your fundamental period captures those two spreads, you're in good shape. So when you look at this picture, think about you know a priori what you're looking for. So you know a priori what your delay and your Doppler spreads are. You size your fundamental period to capture them. If you do that, detection is good. So let's get back to wireless. What we want to do is we want to take these things that happen in the time domain and we want to bring them back to the delay Doppler domain. We want to use the delay Doppler domain as like a control plane. And so up there, I've got my 4 taps that you've seen before. And they act on a pulse in the delay Doppler domain. Here I've just shown you the pulse in the fundamental period. They produce 4 replicas. There's a mathematics of how that happens. It's given by convolution. It's actually not quite, it's given by twisted convolution, which is like convolution with phases. It's not more complicated than convolution, but that's the picture. And the idea is that reflectors act geometrically on signals, right? So we're used in wireless communication to think of using eigenmodes for communication. Here we're not using eigenmodes, we're using geometric modes. They are functions that the channel which nature moves around. So that's a difference. We're going to define something called the crystalline regime, which is the crystallization conditions, which is exactly that the delay period captures the delay spread and the Doppler period captures the Doppler spread. And it will turn out that the interaction of a doubly spread channel with a time domain pulsone is predictable and geometric if we are in the if we're in the crystalline regime. So it's easier to talk about unpredictability than it is to talk about predictability. So when are things unpredictable? Well, here what we've done is we've violated the crystallization conditions by saying that the Doppler spread is bigger than the Doppler period. So this purple ellipse, that's like the channel that's acting on the pulse in the middle. And we're getting self-interaction. So the heavy purple region, that's a region of self-interaction. And the point is that heavy purple region is going to make predictability impossible. How is it going to happen? Well, something will happen to a pulse, to a signal in the heavy purple region. And the something that happens will be a function of two variables. And the two variables will be the two ellipses that are contributing to it. If we were interested in what happened to another point, we'd have another two ellipses and another heavy region. And my point is that you wouldn't be able to predict what happens. Mathematically, it's like having one function of two variables and having a linearly independent function of two variables and trying to predict one from the other. Can't do it. So that's unpredictability. This, of course, is predictability. So what happens inside the fundamental period is just determined by what happens to a single pilot tone. So that's so the idea here is that if you know the input-output relation at a single tone, you can predict what happens anywhere else in the fundamental period. Let me make a picture of that. So here, it's like you sent A, that was your pilot tone. And on the right-hand side, that was what you measured. If you're in the crystalline regime, if the crystallization conditions hold, then if you send B, you'll get that replica. Now, there's a little bit of mathematical sophistication. If you're in a corner, things wrap around. But that's not a mathematical obstacle. Down here at the very bottom, we have inputs X and we have outputs Y, and they're related by an effective channel H. There's this star sigma, which is twisted convolution. But what you should take away is that inputs and outputs are related in a simple deterministic way, which is essentially convolution. But one of the other things that you should notice is that if you're thinking about the received power profile of your signal, it's going to be constant. We're not going to have any of this fading stuff, right? That's in a sense, what we've done is by operating in a certain region, we've transformed the wireless channel into a little Gaussian channel, where all that matters is additive white Gaussian noise. Usually in wireless channels, we don't worry about additive white Gaussian noise, we worry about fading. Here we've gotten rid of fading. We've just got a two-dimensional Gaussian channel. So here I've made a picture of that. What you're looking at is I've taken the fundamental period and I've split it into delay bins and Doppler bins. And I've kept track of the average power of the received delay Doppler domain signal for different values of tau p and nu p. So that's what these columns are. So if you look at the top there, as the delay domain period shrinks, you get frequency selectivity in FDM. Down at the other end, as the Doppler period shrinks, you get time selectivity in TDM. In the middle, you've got, in the crystalline regime, you have no fading, and the received power profile is flat. So that's here's a little illumination of what it means to be predictable. So what we're doing here is we have our fundamental period, and we're sending a pilot tone, which is in the middle of the fundamental period. And then we're looking at the prediction error as we try and estimate the other things in the fundamental period. Here, blue is really good, green is pretty good, yellow is a bit iffy. So you can see that if you're in the crystalline regime, prediction works really well. And so here the idea is that when you're communicating in the crystalline regime, you can predict the entire input-output relation just from what happens to one pilot. Okay, that's when I talk about operating model free, that is what we're going to do. All right, this is the PDM, FDM, pulse zones, good some of the time, good all the time. I want to say just a few words about signal processing. There's a time domain, there's a frequency domain, there's a delay Doppler domain. You navigate from one to the other by applying transforms. Here you're applying the Zach transform that takes you from delay Doppler either to time or to frequency. You can factorize the Fourier transform. The point of this slide is that nothing is more complicated than anything else. It's all essentially Fourier transforms in the end. So again, the details are. So here I'm going to provide a series of slides about. Okay, so here we are. We're thinking about signal to noise ratio, and the signal to noise ratio is just the ratio of the power of the information carrying signal to the noise, and so that's the bottom axis. We've picked a particular channel model, so the vehicular A channel model. And what do we see from this? So what we're doing here is we're moving along the hyperbola. We see that performance approaches TDM as the delay period goes to infinity. So here I'm choosing the size of the period. That's what the legend on the top right does. But performance approaches TDM as the delay period goes to infinity. Performance approaches FDM as the Doppler period goes to infinity. On the graph, that's the blue lines approaching the red line. Okay. The green line says that if you're in the crystalline regime, everything is better. This is more propaganda for give up on estimating channels. Just don't do it. You don't have to. And in fact, here, what I've done is I'm looking at estimating channels versus not estimating the channel. So model free versus model dependent. So yeah, model free versus model dependent. So here I have, it's possible to learn the channel. So I've got a 5-path resolvable channel. The delay Doppler shifts are just integer multiples of 1 over b and 1 over t. So it's a really easy thing to learn. And you see that model dependent performance of the waveform essentially coincides with perfect information. But you see that model free performance is only slightly worse. So predictability is really doing a good job. Okay, now here. What I'm showing is model-free versus model-dependent when it's not possible to learn the channel. So we go back to our vehicular A model, and this top blue line is us trying to learn the channel and failing. So our performance is basically not very good. It's better than TDM and FDM, but it's not good enough that you would care about the difference. The two curves at the bottom one is perfect knowledge, and the one that's just above it is where you're just estimating the input-output relation. You're not estimating the channel. And the story is that you're only slightly inferior. What I haven't shown is that if you're more sophisticated about the transmit and receive filters, so here the transmit filter is just a sink. If you put in a root-raised cosine, it'll do better. You'll leak less energy. What I'm doing in this next slide is I'm experimenting. I fixed the SNR at 16 dB, and I'm playing with the Doppler spread. And when the Doppler spread is close to the Doppler period, then I start to get aliasing. Things start to deteriorate. The probability of error goes west. That's the red curve with the red circles. However, if I am deep in the crystallization regime, that's the blue curve and the black curve, then I can increase the Doppler spread and I'm pretty much impervious. This last one is, it's really a slide about interoperability. So the point of this slide is that a single choice of delay and Doppler period is actually good across multiple sorts of channels. All right, now then, I'll tell a story. So this is the signal processing chain for ZAC OTFS. Blue things mean quasi-periodic. I've written it out in mathematics. At the bottom, you see that continuous inputs actually you see discrete inputs and discrete outputs, but they're related by an effective channel. So it's actually very simple. Now, I have to admit that this ZAC OTFS that I have just described to you was not the first way that OTFS was presented. So Cohere, in its first incarnation, had this idea that they wanted to be a 5G waveform. And so they figured out a way in which to take this waveform and implement it as an overlay over OFDM. And naively, they thought that if they went up to Ericsson and they said, Ericsson, we have a better waveform, Ericsson would say, oh, that's great, let's use it. Actually, Ericsson said, we like our waveform pretty well. Why don't you go away? And so they weren't very successful at getting their waveform into 5G. But to date, most of the academic research on OTFS has been on that overlay. This is what the overlay looks like. So the overlay, I don't expect you to understand all of the things in this box, but basically what the impression I want you to come away with is that it's an unhealthy mixture of periodic and quasi-periodic signal processing. That when you write it out at the bottom, it doesn't simplify to an effective channel times an input. It's weird. If the channel is benign enough, the weirdness doesn't matter. But if you have big Doppler shifts, for example, it does matter. And this is the difference. So the difference is expressed in terms of predictability. So there's the ZAC, if you like, OTFS 2.0, and then there's the MC OTFS, which is OTFS 1.0. And you can see that the 2.0 is doing a much better job of prediction. Let's see how that plays out in bit error rate calculation. So here we are. We are, we're looking at, let's look at the top, first of all. We've got this vehicular A model of the channel, so it's not possible to learn it. We don't have enough bandwidth or time to learn it. Up at the top, that blue curve with the triangles, that's model-dependent MCO-TFS. It's a little bit better. The dotted black line, that's MCO-TFS, and the solid line with the triangles is model-dependent OTFS 2.0. So 2.0 is better than 1.0. It's not enough better that it makes a difference. They're both terrible. At the opposite extreme, at the bottom, you've got perfect knowledge. And if you have perfect knowledge of the channel, everything works. But now, if you don't have knowledge of the channel, if you have to operate model-free, then there's the black squares and there's the blue squares, and the blue squares are better than the black squares. And that's the difference between OTFS 2.0 and OTFS 1.0. All right, so now we've talked about TDM and FDM. Now I want to talk about CDMA. So there's this wonderful quote from Orwell, which I'll read. It says, "Each generation imagines itself to be more intelligent than the one that went before it and wiser than the one that comes after it." So what Orwell is telling us to do is to think back on the generations that we left behind and think about what we liked about them and see if we can get that back. So what I'm describing today, I think of as a triangle. The vertices of the triangle are FDM, TDM, CDMA. And I think of OTFS as sitting in the middle. I've described for you how you can move seamlessly from FDM to TDM by changing the dimension of the period curve. What I'm now going to just hint at is that you can move towards CDMA, so that you can move towards hopping, spreading, low probability of intercept. Let's just keep in mind what we've been describing is we start off in the discrete delay Doppler domain with a quasi-periodic sequence. We lift it to the continuous domain. We apply a continuous domain transmit filter. We transform it to the time domain, and then we go backwards. But there's actually something that we can do before we lift. We can apply a discrete filter in the delayed Doppler domain. And here, this picture. So the little circles, they're the information lattice. So that's what carries the information. The intermediate circles, that's the period lattice. So that's the tau p and nu p separation. And then there's the dual of the information lattice, which is a much coarser lattice. That's the big circles. And what you can, so here, signals are quasi-periodic functions that live on the information lattice. Filters are functions that are, they're just functions defined on the information lattice. So an example is a channel response, that's a filter. Or a reflector response, that's a filter. Some filters actually have no effect. If you put a filter on the dual, it has no effect. And so all the action in filters is on the quotient of the information lattice by its dual. And by choosing things cleverly, you can introduce hopping and spreading. So but that's a subject for another talk. It's not a subject for this talk. So let's conclude. Bad news, good news. Bad news, it's becoming impossible to learn channels. Good news is don't even try. Just try and learn input-output relations. In some sense, what I'm saying is that, when I'm learning an input-output relation, I'm predicting a matrix, right? That's a machine learning thing, right? It's like an AlphaGo problem. So my point here is that if I was designing a physical layer that a machine learning algorithm wanted to see, this would be it. So that's what I mean by opening the door to machine learning. And by the way, it's machine learning that doesn't need a huge training set. I mean, we do machine learning on a frame of what you might think of as OFDM symbols. We do it per frame, right? That's so that's that. Final slide. There you go. Live here you must. All right, thank you very much for your attention.
Well, thank you very much, Dr. Calderbank, and we have time for just a few questions. Any questions from the audience?
Okay.
Pulse zone, if you had a pulse zone that had, it was like a delta function, what would that mean?
Well, I mean, in some sense, it's like we make a little sync function around what would be a delta function. So now we get something that is physically realizable rather than a delta function, which isn't.
Is there something related to an infinite case of a pulsar where it's infinite magnitude and zero?
I don't know. I haven't thought about that. But that's what I will say that I learned something on my trip to Arizona, which was really, really interesting that I didn't know before. It's this. So I learned that this is actually a Gottesman-Kitaya-Pascal pulse in quantum. I didn't know that, but it's. I mean, it makes Woodward all the more remarkable to have anticipated that development.
So I have a question. It might, so I just want to give some context. So I was at UCLA in the early 90s when we were first looking at TDMA and CDMA.
Yep.
And the whole discussion, diversity and fading came up. But the question I have in this context is, so I'm thinking about your 20 questions.
Yep.
And I'm also thinking about this non-model. And so the question I have is, we're using these 5G and 6G constructs. Are there options for frequency choices that could reduce the model? And I'm just going to circle back because I threw a lot of things in there. We have 20 questions, but there's really some finiteness to that when we look at Dopplers, when we look at speeds, when we look at the model. And so in this context, again, I like the non-model and I like the not predicting the channel, but could we reduce the model based on some of the constructs that we're assuming?
Okay. So what I like about this way of thinking is that it starts with what nature gives you, right? Nature gives you a doubly spread channel. You know its delay spread and its Doppler spread. Now we create a world in which that channel acts geometrically. And that's what we use for control. So that's in some sense, I think of that as a minimal thing. What mathematicians and theoretical engineers tend to do is they tend to pick their favorite waveform. It's like, I like Gabor functions. And now I'm going to imagine how to make that work. And these people are really clever. They do make it work, but they make it work in an ad hoc way every time. And it's not a scalable thing. So what I'm suggesting here is that this is a scalable way of doing things. One of the things I mean about Cohere is once it recognized that Ericsson wasn't going to like its waveform, they turned the company into a software company. So what they do is they use the delay Doppler domain to manage wireless systems. And their proposition to carriers is that they double their spectral efficiency, right? So that's only possible because, in some sense, it's a scalable realization. Yeah.
So I had a question about the graphs that you showed. If you are not in the crystalline regime, seems like the input-output relationship is not predictable or not as predictable as it is in the crystalline regime. Do we know, is it impossible to predict when you're not in the crystalline regime, or is there a fundamental limit?
No, I mean, right, so let me go to this thing, right. It is possible to model that really ugly thing at the bottom, right? It is possible to improve. But my point is, why would you want to do that, right? I mean, the thing, when you have these really big Dopplers, your periodic multi-carrier thing starts to degrade. And that's what we're avoiding here.
Yes, I was just wondering if implementing these techniques would impose new demands on device and system technologies, fabrication methods.
So the answer is essentially no, because if you have an infrastructure that's good at doing Fourier transforms, that's all you need. What I will say here is that there's an agenda going on, which is right now, all of the power in wireless resides in the base station. I don't know that the State Department feels that great about where that power lies. And one of the things that they're interested in doing is shifting the balance between the base station and the cloud. Techniques like this Doppler domain control plane, could you use that to move functions like scheduling from the base station to the cloud? That's a really interesting commercial question. Yeah.
Rob, I've got a couple of questions. We've been doing a lot of work on using essentially combs of frequency, which seems to me to mirror pretty much your FDM kind of side of things. And we're using that to expand analysis bandwidth. So in our world, we don't really deal with the channel. We're stimulating it with a known stimulus. We're looking at the response. And so we've been doing a lot of work in expanding bandwidth. So my read of this is that by modulating those combs, essentially you can move from I know what I did to an unpredictable input signal, which is essentially the radar challenge that I know Rich and a bunch of others look at. So that seems to make a lot of logical sense. Is it also therefore logical to say, okay, you were showing all of the performance under a 4-QAM relatively simple signal. Have you looked at 1024 and higher order modulations? And is that just a function of how big the blue box is for unambiguous detection?
I think it is just a function of how big the blue box is. I mean, we wanted to express predictability in terms of probability of error, right? That's and we wanted to do this. We wanted to do the simplest credible thing. We haven't done more complicated things. We haven't done, for example, how you marry coding to, I mean, if I'm, oops, sorry.
Yeah, no, I get where you're headed with that.
Yeah, I mean, if I'm looking at, you know, if I'm looking at this guy and I'm using an LDPC code, I know where I'm putting the parity bits and I know where I'm putting the message bits.
So, and then just a final question: can you talk about the numerical resolution that you're doing your math at? How many bits are you using? A standard double length into real, or are you going into some really detailed domains?
No, we're using standard.
So this is
standard.
just,
I mean, these are MATLAB plots,
okay.
right? They're nothing more sophisticated than
Okay, thanks.
that. Should it still exist? Yeah, absolutely. Yeah.
I had a question on estimation. So for me, it looks natural to use two-dimensional channel estimation. So I have one dimension is tau, the other dimension is nu or ni. And so this is perfect for already existing tool in OFDM. When we do 2D or OFDM channel estimation. So within one OFDM frame, I will have multiple subcarriers. So this will be equivalent to multiple Doppler frequencies. And then in time domain, I will have different OFDM symbols. So I think this will be competitive to the method that you propose.
So what I would say is this: if you tell me that I'm a really smart OFDM engineer, I can beat anything that you do with MCOTFS, I'm not going to fight you. What I am going to say is that if your channel gives you in particular a Doppler spread that introduces self-interaction, you're going to lose. That's what I'm showing in the slides there. But I am not going to say that I can do multi-carrier stuff better than Ericsson, right? Ericsson has really clever engineers. I'm not going down that road. Well, you see, I think that if you tell an Ericsson engineer that it's impossible to do this with OFDM, then Ericsson engineer will throw 7 GPUs at the problem and will get perfect curves. And it's great for Ericsson because, you know, if carriers have to buy 7 GPUs, that's okay. But yeah, there you go. We're
Speaking of buying additional resources, here's a question that was virtually asked. What's your view of 3 most amazing trends coming in tech in the next decade?
So, well, really, our students know that there's only one amazing trend in the world, and that's machine learning. I would say that ChatGPT is interesting, not because it helps students write papers that they'll get too much credit for, but I think it changes programming. It actually changes the balance between Python and compiled programs, because compiled programs are more capable, use perhaps fewer resources. And I have a colleague who teaches cloud computing as an elective, and he was describing how he writes code now. He writes really ugly, approximate code, and then he tells ChatGPT to improve it.
All right, thank you very much, Dr. Calderbank. I see more questions, but I just don't want to, stay between everybody in the lunch. Let's thank our speaker again. It's a wonderful talk. And everybody, you are all invited to join our lunch today. It'll be upstairs on the 6th floor. There'll be more opportunity to network and interact with each other. And also you have more opportunities to talk to our speaker today.